Okay. So the first things I want to do is explain what was going on with, oops. The practice exam in Canvas. So I had to delete assignments. And so we have the 101 exam sample test. Use this to register for the in-person exam. Now, for this particular exam on the 23rd, you all did that. So I just leave it there for you or what comes after. The other thing should be the 101 practice, and you use this to see multiple versions of the exam, but the scores aren't saved. So this is just for your practice. I'll click on it. And we see, oh, here's a first order problem, and all the problems are there for you to see, right? And then let's say, all right, wow, I did great, but are there some problems I haven't seen? So you go over here and you click on new version, and then you can see that the problems are somewhat scrambled. And actually, I can kind of show you what's really supposed to be happening. What is the kind of the thought process is that there's group one, and it chooses 6 of these questions from here, and it doesn't repeat them or without replacement. All right. Then it will choose 6 of these, and the transient ones are, first or second order. Then some of these AC problems, which are all pretty much about complex number manipulation. Then it'll choose 5 from what is called DC, but many are, I could call it op-amp type applications. And it chooses what? 5 out of that many. Then there's 2 from basic concepts. Again, it's it's just 4 questions from there. Then I have another applications section, which like this one is really, it's kind of like a node, just starting nodal analysis. That would be a mesh. Then we're starting in on some circuit analysis. So this one's very much nodal and mesh questions. Even though this particular one has an op amp, you're really just summing the node there. Right, then we have, that's a mesh. Then we have the various Laplace transforms, and then we have the various RMS things. Any questions so far? Let me see. Okay. All right. So I had been really thinking about that when, at least when I'm teaching a problem, we have various, oops, actually, various kinds of problems. We might have an RC, and it's a step. Now, usually for the 101, they're doing this kind of switch thing. Or we have this kind of problem. With RL. And we can do a step. Now, how is that step achieved? Usually we have some kind of switch that's opening or closing that either sets the external current to 0 or opens it up. But in 110, usually you just have things that are a step. You turn the voltage on, you turn the current source on. But anyway, and what can happen is I can get really bogged down in like a very formal solution that might just be too much to remember on an exam. And so I'm really trying to think about, you know, what's going on in an RC or what's going on in an R. Oh, even I messed that up. Ugh. Or in an RL circuit. So this right now, I'm just going to try. I think I found a way that hopefully that it's just easier to remember. All right. And I'm not quite sure what it is, but it just seems that RC circuits are easier to remember because you're really filling up some container with water through a hose that has some resistance, right? And the energy stored is basically based on the height, right? But also the diameter of this. The bigger the diameter, the more energy storage. And first order circuits all have exponential decay in them somewhere, right? This is the fundamental thing. And the trick is what is the RC time constant of a particular circuit? So now you can go through and derive out and take the inverse Laplace transform and get that, but maybe that's just too much for the exam. So I try to remember things physically. The larger the capacitor, right, the bigger the area, the longer it will take to drain or fill this, right, area of the can. The larger the resistor, the slower it will take to fill. Well, the bigger C, right, will cause it to take more time to get to a certain spot. The bigger the R, it'll take more time to get to a certain spot. And the smaller these are, right, the less time it'll take. And so maybe, you know, at some point, right, we're just memorizing, oops, that. All right. Now, if we do the inductor, inductors are a little bit harder, and you can even see that I was trying to research better analogies. This is my horrid picture of an inductor. So I have water flowing in this inductor, right? Or in this bent tube, right? And the energy is stored basically because you can just think of it as that the water, as it's going through, is spinning around, right? And like a flywheel, because flywheels and inductors are mechanical analogs of each other, right? So then, but the energy is stored in the movement, and then the resistor slows that movement down, right? So what happens is the bigger the R, the more that movement is slowed down, right? So now it is in the numerator, but energy storage will always be in the denominator. So the bigger the L, the more energy storage there is. All right. So, you know, is this, I was trying to come up with mnemonics or a poem or even a song so that this could be, I just haven't gotten to it yet. But anyway, everything has exponential decay, but how is it scaled? RC is minus T divided by RC, and then RL, it's E to T times R divided by L, right? And so, 1 over RC equals this, R over L, right? Now, the thing is storage is always in the denominator. More storage means more time to do anything, right? Now, in the capacitor, right, it's slowing, the bigger it is, it's slowing down the energy storage of how fast something fills up or drains. But in the inductor, the R stops flow. So the bigger the R, the quicker it will stop the flow. And so we have that. All right. So really, in all these problems, we're trying to figure out where does it start, where does it end, and how long does it take to get there, right? And over time, right? And for first order, right, we can kind of come up, that's exponential approach, and that's kind of a 1 minus e to the minus t type function. And then many times we just have exponential decay, which is something e to the minus t. Now, it's true that these numbers can change because you can get curves. If I have a minus this, right, I could have something that looks like that. But really, for these questions, it's really one or the other. Sorry about this. Just trying to get. So we all want to find out where does it start, Where does it end? And how long? So let's yeah, this is a tricky one. So you can do things in a full-blown circuit manner, or you can do them intuitively. And in fact, I suggest you kind of figure out what you want to do intuitively, or how it should behave intuitively, and then maybe do it more formally, or do it formally, and then check your intuition. But here we have IT. That's basically what we want to find over time. All right. So where are we going to start? So at time equals 0, the switch is going to close. So that means it's open before that time. All of this current will be flowing between R1 and this path. All right. Now, the thing to remember about that inductor is that when there's no change in voltage, right, that means there'll be no change in current, and that means the voltage across that will be 0. So it acts like a short circuit before that switch is closed. All right. So I could redraw this where I have the current source, and I'm just not even going to bother with the switch. I have R1, and I have R2, because that's at 0. All right. Well, there is a relationship called current division, right? And so IR2, right? Well, here's the thing, right? If this is bigger, more current will go through R2. So this should be R1 divided by the sum R1 plus R2, right? Now, if you happen to forget that, right, we can just call this node V, right? Or we can, well, we can just do a nodal analysis, right? So we have I naught equals IR1 plus IR2 would equal V divided by R1 plus V divided by R2, right? I naught divided by V is 1 over R1 plus 1 over R2. or I should have just left that there. I not. Okay. Then IR2 equals the voltage, I naught 1 over R1 plus 1, 2, oops. All right, that's the V divided by 1 over R2. All right. And then you can take it from there. I don't want to spend too much time on that. But that's pretty much would tell us where the starting point was. All right. So in this case, we're going to start up here. All right. And then we're going to end somewhere. Where are we going to end? Well, we close the switch, and then all the current is going to go through here. And not only that, when the switch is closed, this spot and this spot, it's shorted. So there's nothing that's going to flow through R1, right? So in fact, this side here will be tied to ground, and all the energy that's stored here will eventually drain away, and so that we're going to end somewhere at 0. And the only thing that can do that in a first order system, excuse my, is some kind of e to the minus t. Now then the trick is how long will it take? All right, how long will it take? So as I said, this current switch is now closed, right? That's R1. If you had a choice, which way would you go if you're current? Through 0 ohms or through any kind of ohm? So this really isn't going to be there, right? It just doesn't exist. But also, right, this part here, right, this switch ties these two nodes together, right? And so really I'm going to have R and L, all right? And right from here, you can say, well, I have an R and I have an L, then I have to have exponential decay is going to be in there somewhere. Then you could just either remember this like we talked about, right? Or at that point, you can even use kind of a modified Laplace method, right? Where we use impedance. We have R, the impedance of an inductor is SL, right? We can do, oh, I see you raise your hand, Nathan.
Yeah,
Okay.
sorry.
No, that's
So
great.
when you say that when the switch closes,
Yeah.
why does it why does the inductor equation only account for the second resistor? Why does it not count resistor one as in a series?
Okay. So, why does closed switch I don't know, get rid of R1,
Yeah,
right?
that's a fair way. Yeah.
I mean, no, sometimes my way of speaking is very intuitive, but so let's do this, okay? And our equivalent, right?
Yeah.
Our equivalent, and I'm just going to do the shorthand for parallel R1, R2, R1 plus R2. Now, in this case, let R1 go to 0, right? And let's say R2, I'm just going to say 10, right? So we'll start off at 10 times 10, 10 plus 10, right?
Hmm.
Would give us 5, right?
Oh yeah.
But then now we're going to go 1 times 10, 1 plus 10, and what is that? 10 divided by 11, right? Which is getting close to 1, right?
Yeah.
Okay. Then 0.01 times 10, 0.01 plus 10. So this is 0.1 divided by 10.01. So it's actually starting to approach whatever the smallest value is, right?
Right.
So if then I just plug in 0 times 10, 0 plus 10, right? The
Hmm.
equivalent resistance is 0.
Okay.
So looking this way, right, these two parallel paths, right? Let's just keep it drawn. Let's draw it back, right? Sorry, this is L, R2, R1, right? So let me put in this RS for R short, right?
Okay.
So this is getting smaller and smaller and smaller till eventually all the current flows through here and the equivalent resistance is 0, which really means
Oh,
you've just shorted it. Oop,
I see.
okay.
Okay.
Yeah, and that's a really good question because sometimes we do things and we kind of forget why or like really get what is a parallel circuit. Oh
Right.
yeah, sure, people can remember that, but like sometimes in my mind I'm just imagining I'm some electrons going this way or going that way. And I've known students sometimes even in 122 that this explanation helps. So it's better yeah, it's better to get it now.
Yeah.
Now, yeah, but the thing is, yeah, I guess is part of me is that if I, like back here, from a mathematical nodal analysis, right, if I have, I think I think it's time for another layer, is that if, you know, you need elements, right, to separate things, right? Otherwise, it's all on the same node. So this area here, as long as it is, mathematically is one point in space. It's one node. And usually we call it, ground. Then we have another node here, and it's equal to, measured from, we measure our node voltages from the node to ground, right? Then we have another node here, I'll call 2, 3, 4. Node 5 is really ground. And so V2 is really V2 minus V GND. V3 is V3 minus, everything's measured with respect to ground, where like VR is measured across across the device. So that when I go and put like a wire across something, right? This is in nodal analysis, right? It's a 0 ohm wire, right? And it has no, and so really, here's node 1, here's node 2, but there's nothing really separating it anymore. So in fact, now in LT Spice, I think it'll randomly delete one of these nodes for you. So, let's say you've called this V out, but by accident, you've grounded it. V out will disappear and it'll label it ground. But yeah, maybe this is a better physical way to remember that. Okay. Now, I think we need to come back, and we were going to find out what the time constant was. Now, yeah, maybe, we all hate to say, don't memorize it. You don't really learn it that way. But I don't know, some things kind of, maybe they do need to be memorized. But if you can't, right, and yeah, all of a sudden, if I haven't done these problems in a month, I start to lose it as well, right? So let's do a nodal analysis, plus, minus. IR1, or that was 2, plus IL equals 0. I'm just going to label that V, right? So V divided by R2 plus V divided by SL, because we're doing it in impedance now, right? And that means like we've kind of taken the Laplace transform, all right, equals 0. So we got to find out where S equals 0 will actually tell us what the time constant will be. So we collect the V, right? And here's the thing: if the voltage over time, or the Laplace voltage, were 0, right? There wouldn't be any current flow. There'd be no. The problem would be what is known as boring, because there'd be nothing to discuss, right? So we just get rid of it. So all we have to do is find out where that equals 0. And Now, why do we get that minus sign? Oh, that was the previous. We get that minus sign because really it's kind of like e to the t s. And yeah, I know the Laplace transform, it has a real number plus an imaginary number, but sometimes they use an s here, right? So now it would be e to the minus r l t, which gives us exponential decay. In 110, we go over how to use the Laplace transform a little bit more, but this is prepping us for that. Oh, okay. Hi, Steve. We have Steve, Robert. Okay. Now, just for those of you who weren't here at the beginning, I have been recording this, and I will post it, a link to it on the in the Canvas show. Now, I know it might be hard for you to say, well, ask me this question. So what I'll do is I'll just scroll through slowly, and maybe you can raise your hand or somehow let me know that that's a problem you want to do. All right. I think that's the one we just did. Okay. Oh, is that a hand? Oh, it's a chat. Okay. Forced voltage response. I don't see why not. File. Save. All right. Do you mean this one right here? Where's your chat? In my mind, this switch closing is like a step response, so you're forcing a voltage. Is that the one you mean? Oh, no. I kind of need more. I need more info, right? Because the thing is this starts off at 0, switch closes, and it will charge up to V naught. You're, in my mind, one below. All right, has a current equation with a cosine. All right. This one? One of the below questions has a current equation with a cosine. I think I know the one you mean. But it's not popping up on this test. So I just regenerated it. The phasor voltage, the phasor voltage. Sorry. Da, 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 da. Sorry. Oh, okay. Okay. I think it's this one where I have a current and I source of T equals 3 square root of 2 cosine 8T amps. Okay. All right. Is this right? Okay. All right. All right. So here's the thing. I can put VT here plus minus because really I'm measuring it from here or here or here or here or here or here, right? I can even say that VT plus or minus is here because it's all this node to that node. All right. So we'll call that R1, L, or we'll just call that RL and C. So really, what we're looking for is, V equals IZ. Equivalent. All right. So really, what is Z equivalent just looking into this? Okay. So, if I had my impedance analyzer, which I do in my office, right, what is that equivalently? Well, I have two paths, they're in parallel. So it's R1 in parallel with ZC plus ZL, all right? And so then we get R1 in parallel with 1 over SC plus SL. This is so we let S equal J omega when the whole idea is that we have a persistent sine wave of some frequency omega. And in this question, it was cosine 8t. So in fact, that is our omega right there. All right. So J omega equals 8J. All right. So let me just pull it out here. So 1 over SC equals 1 over J 8. The capacitance value in this problem 0.00892. Right. Now the thing is since we need to add these two, it's better just to keep them in Cartesian coordinates, right? And then SL would be J8, and in this problem it's 0.75. All right. Now at this point, it's better to like you might try to keep it all in equation format, but I just need to use my calculator. So 1 divided by 8 divided by 0.0089. So we get 14 point. So we get 14 point. I think it was. Oh, sorry, my memory. 0.045 ohms. Now, something that, yeah, you really have to memorize that 1 over J is going to be minus J. All right. Then this is going to be plus 6J ohms. So ZC plus ZL in this case is going to be minus 8.045J. So we'll just switch colors. Oop. So Z equivalent equaled R1 in parallel with minus 8.045 J. I'm just leaving the ohms off because I'm in a hurry. And so R in this problem equals 8. All right. So that Z equivalent is going to be equal to 8 times minus 8.045 J 8 minus 8.045 J. So this is minus 64.36 J, and this remains the same. All right. Now, I'm sure you could just plug this into, an imaginary number calculator. I guess I always do it out and try to draw little pictures of what I'm doing. All right. So, because it's just really easy to kind of make a mistake. So when you're adding, you use Cartesians. When you're multiplying, dividing, you use polar. So this becomes 64.36 magnitude, right, at an angle of minus J is minus 90, right? And yeah, what do? I tend to say, all right, here's my imaginary, there's my real axis. I have one number down here at minus 64.36. What's the vector to that, right? Minus 90, right? Now, here, right, I'm going to have, I go over plus 8, but then down minus 0.8. So it's very close to minus 45, right? So some of these problems you kind of do have to take out a few decimal points. Although I think looking at the answers, everything's in these nice round numbers. This is almost equal to minus 64J, 8 minus 8J. All right. But just in case that's not we can't do that, I'm just going to carry this out. So really, Z equivalent equals 64.36 minus 90, right? Where did that minus sign go, right? Well, the J is on the imaginary axis and the minus sign brings it here. So it's in the minus 90, right? Let me just hold on. 8 squared plus 8. So the magnitude of this is 11.35, right? Because the magnitude would be equal to 8 squared plus 8.045 squared divided by the square root. And something I just remembered is that it's the real squared plus the imaginary squared. Even though there's a j here, right, that just means that's the imaginary number. You don't actually square that imaginary number. It's just, the imaginary means just pull out this. The real just means pull out that. Real, imaginary. All right. Then the angle. Is all right. All right, now we just so the magnitudes we just scale. And so we have minus 90 minus 45 degrees. Which gives us 45, 5.670. Right. Now we almost might have forgotten what we've been doing by this time. All right. But remember, the V equaled I times Z equivalent. The I was 3 divided by the square root of 2 times 5.670. Which is very close to 12, right? Now, how do we handle, it gives you a choice of things, right? Now the cosine, it's still gonna have 8t, but now we have just to have the phase, and so you just put the minus 45 degrees, and that would be the answer. Was there a, oh, 0.6. Okay. It might be better to like raise hand because I think I kept talking for quite a long time. Get the 0.16. 16? Is it 0.16 or 16? Where? I mean, I have 64.36, 11.35. Oh, this right here? Ah, okay. All right. Okay. Um, sorry about that. Um, okay, so I was out at 8, and then I was at minus 8.045. Right. So I should have been able to do A tan minus 8.045 divided by 8. That should have given me that answer. Now, I think if you used all the digits of precision, you would have gotten 12. All right. Let me see. Was that? I'll just double check that calculation. Yeah. It's because I didn't use 8. Right. If it, if I had done this, right, that's where that comes from. Okay. I think I answered that one. Any other questions? Because that one is probably one of the hardest ones of that brand, right? Now, yeah, back to the transients. Probably one that gives people a lot of trouble is this one. The switch closes and it's an ideal voltage source. So this V naught from here to here is from here to here is here to here. And even though there is a current through here, it does not affect the charging of this circuit. And so you get, the time constant is R2 and is composed of these two. All right. Might have, are there any objections to me doing this, or do you have another question, or? Okay, we still have the same bunch. Okay. So as we've talked about, right, these first order problems are always going to have some kind of e to the minus t. And then the question is, and yeah, you can even memorize this, but depending on the configuration, these might be in series, they might be in parallel. What is the equivalent RC time constant? All right, but let's just go over the whole thing. So where are we going to start? Where are we going to end? How long? All right. So this switch is open, and any charge in here is going to dissipate through R1 and R2 so that any energy stored in that capacitor will be discharged to zero. So that's our start, right? We start at zero, right? Now, where are we going to end? So this comes down, right? And you might be thinking, well, there's a voltage division, or is that current happening? But really, if you remember, what is an ideal voltage supply? It can supply any voltage regardless of what it's driving. And maybe if I redrew this a little bit down here, it'd be easier to see. Okay. So see how this is all at the same. That's all the same node. So whatever the voltage is, here is here is here is here is here. So while it's true, there's a current going that way and there's a current going that way. This node isn't unknown, right? Especially, let me pop in a ground there, right? That node is measured from here to here. There's an ideal voltage supply when the switch is closed that makes that whole node everything. So it's not unknown. So the only unknown node is this right here, all right? So it's going to end, right? So even though, yeah, there will be current flowing through here, right? The current's going to charge through here, and then at some point, it's just going to fill it up. The current drops to zero, so there's no voltage drop across the RL after time. And so way out here is V naught, right? And there's only one curve that's going to do that, which is 1 minus E to the minus T. Because this keeps going, it doesn't change at some point. If I were doing exponential, right, increase, it would just keep going forever. So it has to be of this form, all right? Now, again, from this point of view, all right, there really is only one node to solve for, and that's that node right there. And yeah, I like to use the impedance method. So this is 1 over SC. That's still R2. All right. Um, I'm going to call this, actually, I'm going to call this node 1, and I'm going to call that node 2, right? So I have R2, voltage drop, C, and that's already given to us in the voltage drop. So IR2, right, equals IC V1 minus V2 divided by R2 equals V2 divided by 1 over SC. V1 equals V2. So while this form, it's mathematically correct, it really is best to have S on its own. So I am going to pull out a C, right? And I'll get S plus and you can see that where does that equal 0? Minus 1 over R2C. So that 1 minus e to the minus t R2C times V naught. Now, this problem has kind of its opposite number, all right, where the switch is closed and it opens at t equals 0. So where does that start? All right, so if the switch is closed, yep, there's current flowing through R1, but there's no current flowing through here because the capacitor is already charged, right? If this has been charging for a long time, it starts at V naught, right? Because in these first order circuits, either you charge up to something and stay constant. Constant is DC. Capacitors are open at DC. Or you discharge down to 0 and then it never changes. So after a long time, right, these capacitors go open, and that means no current can flow. If no current can flow, there's no voltage drop. So therefore, we start at V naught. Now, when that switch opens, there's no external power supply. And where's that current going to go? It's going to discharge. And here's the trick. It discharges through both. So if I redraw this circuit with the switch open, right, I have this, right? Well, I can just combine that And then here's our standard RC circuit, except now we can tell it's e to the minus t r1 plus r2 c. And we have to scale it by v naught. Any other questions? I think there were some problems where you might not have been getting access to the whole bank, right? So eventually, come Tuesday, you should be able to see, just like I'm doing. Now, with this particular test where you can just keep creating your own versions, right? It'll tell you how you do, but it won't save any score, right? So I'm just going to check that out by I'm just randomly selecting answers, right? All right, so now here's the thing. If you save your answers, it just saves it and you come back. Submitting should tell you everything that happened. Okay. So yeah, there's no problem for you to keep track of what those questions are. You can cut and paste so that you can see, and that's just random, right? And it looks like try similar problems for all questions with less than perfect, or you can then now create a new version, right? And go through there, right? If you do and this is for the future, again, you guys have done this part where this is the sample test that it will save the score, and I would need to see an 80 so that you could take the exam, right? Notice on this one, there's just no place for you to create a new exam. But this one, the scores are saved, and you can just see these other problems. But those were kind of the big ones, I think, that historically people have had trouble with. Okay, I'm going to need a real question or something. Otherwise, I'll let you guys go and you can go study up. And I'll just see you Tuesday. Okay. Now, do you mean just finding the Laplace transform? Like, do you mean those problems? Okay, yes. All right, let's find one. Okay. So f of t in this case is 6t e to the minus 7t. All right. And we can just say, the Fourier transform of that is 0 to infinity ft times e to the minus st dt. Oh, let's see. Oh. All right. Any objections to that? I'm still practicing my drawing on Wacom tablet with mathematical things. I know it's a bit sloppy. So, integrations of exponentials should be easy, but we're kind of multiplying it by t, right? So does anybody remember that what you have to do when you're doing that kind of integration? What the technique is, unless you just have it memorized? Does anybody want to say, or?
Are you supposed
Oh,
to
can you
get?
speak up?
Oh, hello?
Yes.
Are you supposed to get the derivative t multiplied by e to the negative 7t, and then add that to the derivative of e to
Okay.
the,
So what is that called?
I actually forgot what it was
Okay.
called.
All right. No, that's okay. Because integration by parts, which you would have, let's see, uv, oh man, minus the integral of v du. Now, I think what I always struggled with is, well, what's going to be v and what's going to be the du? But the trick is we got to make sure that we don't end up with t multiplied something t to some power times an exponential with t in it, right? So if I choose u to be e to the minus 7 plus S T, du would be minus 7 plus S e to the minus 7 plus S T. Now, if I chose U to be this bit, right, that means dV equals T, and that means V equals T squared divided by 2, which means I've just made it worse, right? Okay, so that didn't work. So let's choose U to equal T du equals 1, dV equals e to the minus 7 minus S T. Okay, and then that means V equals, I take what I started with, right? And I have to, in order, like if I took the derivative, what would I have to put there to make sure that that didn't happen? Or I mean, I got rid of it. So I would have minus 7 minus S. Okay, all right. Now I should be able to do everything. So even though I think sometimes what people forget, especially in the documentation, is that they just put this formula. Oh, yeah, what's up, Nathan?
Isn't that supposed to be 7 plus S? Or was it supposed to be negative,
Oh,
right?
no, where did I go wrong? But I got minus 7 here, right?
Yeah.
And I have minus S there, right?
Yes.
So minus ST, minus 7. Oh, all right. Sorry. You're just talking about that.
Yeah.
Okay. All right. Thanks.
Okay, no problem.
No, that's great. Then I have the minus sign, integral. Now V du. And sometimes they just show U times V, but that really means you do have to evaluate it. All right, so U is T, and V is e to the minus 7 plus S T 7 plus S, and I need to have a minus sign, 0, infinity. So at infinity, right, this is getting very big, but this is exponentially getting very small, right? So it should go to 0, right? Then at 0, right, this makes this 1, but 1 times 0 is still 0. So we get rid of it, right? Minus, and where are we? We're du is 1. V is e to the minus, and I'm going to switch this 7 plus s. I mean, set s plus 7 t divided by, I'm going to put the minus sign here, and s plus 7, right? So that's already 0. Now we're going to have minus here. And so oh, well, first we have to integrate it. And when we integrate this, we have to get back to where we come from if we took the derivative of it. So we get s plus 7 squared. Because if I took the derivative of this, I'd bring this down. That would cancel out one of the s plus 7s, and that minus sign so if that's positive, all right, because I take that down, that becomes positive, all right? Infinity drives that all to 0. Putting this at 0 makes that 1. Um, oh, okay. There was a 6 in there all along, which I had forgotten about. Okay. So to me, that's one of the hardest ones because you really have to remember integration by parts. And yeah, that's part of what the 101 about is making you go back and review things so that when we use them in 110, we're not having to struggle to remember things. But yeah, probably the most important ones, like 2, is really just a step function. So that one's fairly straightforward. The ramp, right? That's just a straight ramp. And so you get t times an exponential. That one needs integration by parts. Exponential decay, you just have an exponent times the exponent, and that's probably the easiest one because you're just integrating an exponential. This one, really, you just break it up into 2, where you have an exponential, right, and then that's a step. So you're in it, you're transforming a constant, you're transforming a decaying exponential. So you just do it twice, where you just break it up, right? Oh, that's the one we just did. Double exponential. Well, really, you just take the Laplace of this one plus the Laplace of that one because it's a linear operation. Asymptotic double. So you just break it up. Here's the constant. You do the Laplace transform of that, the Laplace transform of that one, and the Laplace transform of that one. You just sum them up. And asymptotically critically damped. Yeah, I guess this one's the hardest one because you have to do the Laplace transform of a constant, an exponential decay, and then this ramp-like thing, which needs integration by parts. I think I have time for one more question. Oh, I didn't see this here. Uh, oh, okay. So, all right. Let's see. Okay. I think I do have a lot. So the question is, what about RLC? And I'm pretty sure I have videos in my channel about that. So yeah, here's so series RLC form of natural response. Okay, so I do, and yeah, it can take about 10 minutes to answer, but there is a video there. I do kind of answer that in a video there, but so I'd rather not redo it. Is that okay? Oh yeah, okay, yeah. All right, so it's okay. All right, thanks. Oh, how about the average voltage? Average voltage. Do you mean RMS, Robert? Oh, okay. All right. I'm going to answer this one somewhat generically, though. All right. So really, in the book, they call it XRMS equals the square root of 1 over t, 0 to t, and whatever the signal happens to be. If it's voltage, then we use voltage squared dt. And just let me double check. Yeah. Although, yeah, I guess in the question, since we're saying that's XRMS, I should have an X there. So really, we have kind of several kinds of problems. All right. One is just a pulse width modulated signal. All right. So we can call that V1 and V2. And this right here, for example, a quarter T. All right. Well, it's best to kind of break things up, right, before you start, or just draw a picture to make sure that you know what you're doing. All right. But really, since we're integrating V squared, right, we actually get, now these aren't drawn to scale, right, but it's V1 squared, V2 squared, and it doesn't change. And in this example, it doesn't change that. So in fact, there's two integrations that we want to do. All right. And a lot of times I take care of the integration on its own. So I go from 0 to a quarter t. What am I integrating? V1 squared, which is a constant, dt. Oh, even I messed this up. It's squared, right? So it's both positive. And this would be from a quarter t, 2t, v2 dt. All right. Now this part, I mean, it's easy, right? 0 to a quarter t, v1 squared. Now, So again, it's t, but sometimes what I do is I transform that part and saying, well, from a quarter t to t, I mean, it's just a constant, right? It's really the same thing as v2 squared 0 to 3/4 t, right? You should get the same answer. Sometimes that's helpful, sometimes it's not. All right, but once you find these two numbers, then you scale everything by the whole period, and then take the square root. All right. Now, the other one, right? It's usually something like this. All right. Well, you might think to yourself, well, I'll do the same thing. I'll break it up, right? And there's some kind of slope there, right? MT, but the line starts at 0 and goes up, plus, plus something else, and that goes from 1/2 t to t. But the thing is the equation of this line is different, right? This line has an offset in the b, so not only that, it's going to be like minus mt plus b squared dt, which is kind of annoying, right? Well, let's just make our life easier and say, what are we really integrating, right? So that's going to be vp squared, right? And it's symmetric. So if I integrate from here to here and multiply by 2, right, that should be pretty good. So that will give me 2 divided by the period, 0 to 1/2 t. Now, because not that, it's hard to find, the intercept, but it's just one more thing that you have to do, right? So by finding this area, multiplying it by 2, and then doing the square root of it, there you go. Now there's another triangle one where it doesn't start at 0. All right. So this picture should be in the question, right? And it's symmetric. So that could be minus v. We'll call it VP, right? And so it's just the way these work is that that'll be at a quarter t. Excuse me. That's 1/2 t, 3/4 t, and at t. So what are we really integrating? We're integrating the square of that, right? So this becomes, something purported. That's ugly. Something proportional to like a decaying exponential. Then we have this, so that would be VP squared. VP squared comes back down and goes back up. VP squared, right? This is I believe at a quarter, 3/4, and I look at it and say, what is the easiest thing for me to integrate? Because look, this area is going to be equal to this area, equal to this, equal to this, even though I know my drawing is kind of lousy, right? Well, so again, I just make my life easy, and that, yeah, I can just multiply 4 times the period and go 1/4 t to 1/2 t, right? But I would still have to do some kind of offset. So I'm going to change the x-axis here, right? So instead of 1/4 to 3/4, well, I'm just going to go from 0 to here and then use whatever that slope is. You know, you find the slope from here, right? There's some m, right? All right. So this one is the trickiest, but really you draw out it, then you square it and say, what am I integrating? Then, you know, can you just integrate 1/4 of it and multiply by 4th, integrate 1/2 and multiply that, or whatever after that. But then I transform the time axis and go from there. Okay, so the question is, why am I multiplying it by 4, right? Because I'm not integrating this plus this plus this plus this. I am only integrating this area, right? And so I'll call that A1, A2, A3, and area 4, right? I know I have it drawn it that way, but they are equal to each other because this is symmetric. It's minus VP plus VP. If I square it, it's going to come down. I square that, it's going to come up, come back down, and then come back up, right? So I'm only going to do one of these areas, but so I'll put it this way, is that A2 equals A1 equals A3 equals A4, right? But really, what the total integration would be A1 plus A2 plus A3 plus A4, right? Which also equals, if I take that's equation 1, that's equation 2, right? Substitute 1 and a 2 and combine 4 divided by T, A2, area 2 is this, all right? If, and notice, yeah, I went from 1/4 to 0 and from 1/2 to a quarter, because really, what is that equation that I'm integrating, right? Oops. What is the, So what that is here's 1/4 t, 1/2 t. Right? It's 0 up to here, and then it becomes mt squared, which, while you could model that mathematically, you don't want to get into that. So you just say, oh, it will be mt squared if that's at 0 and that's at 1/4 t. Now, yeah, why don't I put the sine wave? Because that one is a really long derivation. And yeah, if that's VP, RMS should be that divided by the square root of 2. Okay. Should just kind of have that one memorized. Okay, so what is the slope? All right. All right, what's the slope? So there's two problems. One where you start at 0, go up to V peak, right? And you have 1/2. Well, really, m is going to be equal to the rise, Vp minus 0, divided by the run, 1/2 t minus 0, right, which is what? 2 Vp divided by t. Then we have the other problem, right, where I might have used different labels, right? And you can see that's 1/4 t, right? So you can do it from here to here to here or here to here. But what is the rise? You're going from, in this case, 0 minus Vp. What is the run? 1/4 t minus 0, which would equal to 4 t. All right. So while the voltage is in there, no, it's really the slope. Oh, well, thank you for asking that question. All right, guys. I'm kind of getting hungry, so I'm going to end the meeting. But you can just email me a question, and I can't guarantee to answer it, but I will do my best, and I hope to see you bright-eyed and bushy-tailed on Tuesday. And my final word of advice is, don't stay up late doing problems. Just go to sleep. I think you really do know all this stuff. You just have to kind of get it back into your head, right? Anyway, goodbye. I'm gonna end the meeting. Okay. Let's see. Okay. How do I do that? End meeting.